All right. Hello and welcome once again to um, our series of teaching on the JAM syllabus, past question, chemistry past question to be precise. Um, Today we are going to be looking at the 2016 JAM past question. We are going to be looking at the topic, the questions, and we'll look at the options together. And I'll tell you reason why we choose certain option has the right or the correct answer. But while I do that, I want you to also endeavor to participate. So I'll be requesting that you tell me in the comment section what you feel the right answer is, so that I'll be able to know if you understand the concept, and then you can apply them when you see questions from the past question that we'll be treating. So we're looking at the 2016 JAM past question. I remain your tutor, your teacher, Anjorin Oluwafemi Excel. And without much ado, let's quickly move into the first question that we have here. So the first question says that in an electrochemical cell, polarization is caused by A, oxygen, B, hydrogen, C, tetraisosulfate 4 acid, D, chlorine. So what causes polarization in an electrochemical cell? Let me have your response in the comment section. And then I'll reveal the answer and tell you the reason why the answer that was chosen was picked, So the answer to this question is hydrogen. In an electrochemical cell, polarization is caused by hydrogen. And the reason is because polarization occurs when hydrogen gas accumulates on the electrodes. When hydrogen gas accumulates on the electrode, especially the cathode, during electrolysis, forming a barrier that impedes the flow of electrons. So that is what happens. Hydrogen gas accumulates on the electrode, especially on the cathode. Then it forms a barrier that impedes the flow of electrons. Okay, so that's the answer to the first question that we have there. The second question goes like this. It says the condition required for corrosion to take place is the presence of the condition required for corrosion to take place is the presence of A, oxygen and carbon dioxide, water and oxygen, water and carbon dioxide, water and carbon dioxide. Okay, so C is water, carbon dioxide, and oxygen. Okay, so let's look at all the options that we have here, and let's see which do you think is the reason or the condition that would facilitate corrosion to take place, Is it A, B, C, or D? So let me know what you feel the right answer is in the comment section, and then you can be able to compare to the question to the answer that I'm going to be revealing and the explanation that I'm going to be giving to you for picking this answer. Okay, so the answer is actually B, water and oxygen. Now, the presence of water and oxygen facilitates or aids corrosion. Corrosion, especially rusting of iron, requires both water and oxygen. This facilitates the electrochemical reaction that leads to the formation of rust. So water and oxygen is a condition that is required for corrosion. Okay. So if you have chosen the answer B, then you are very, very correct. Moving along now to question number 3, says that the enzyme used in the hydrolysis of starch to dextrin and maltose is A, zymase, B, sucrase, C, amylase, D, lactase. What do you feel the answer is to this? Is it zymase, is it amylase, is it lactase, or sucrase? Okay, you know the routine. put your response in the comment section and then see the answer that I'm going to choose and then the reason for choosing the answer. Okay, is amylase, which is C. Amylase is the enzyme that is used in the hydrolysis of starch to dextrin. And amylase breaks down starch into simpler sugars such as dextrin and maltose during digestion or industrial processing. So amylase it is then. Amylase is the right answer for this question. Question number 4 says that in the laboratory, preparation of chlorine from concentrated hydrochloric acid in the presence of potassium tetraoxomanganate 7. The product is dried by passing it through. The product is dried by passing it through A, concentrated tetraoxosulfate 6 acid, B, anhydrous calcium chloride, C, calcium oxide, D, sodium hydroxide. Okay. The answer to this one is actually what now? Can you tell me in the comment section what do you think the answer to this is? Is it A? Is it B? Is it C or D? Okay. All right. So the answer to this is actually A, concentrated tetraoxosulfate 6 acid. That is what we use for the drying process, for drying the product that is gotten when we prepare chlorine in the laboratory. So concentrated H2SO4 is a strong dehydrating agent and it is used to dry chlorine gas by removing moisture. So that is the answer to this one. The fifth question says that the monomer of nylon is the monomer of nylon. Don't forget that nylon is a polymer. So there are other units that comes together, smaller unit that now forms the polymer nylon. So the question is the monomer of nylon is A, is it hydroxybenzene, B, hexane dioic acid, C, benzene 1,4-dicarboxylic acid, or D, ethane 1,2-diol. So please let me know what you feel the right answer is in the comment section. And okay, so this is what we have here. The answer is hexane dioic acid is the monomer for nylon. Nylon 6 is made from condensation reaction of hexane dioic acid and hexamethylene diamine, forming a polyamide. So that's the what's it called? That's the answer to that. So please let's take note of that. So hexane dioic acid, it is then what we use for. Okay, is what we use in combination with hexamethylene diamine, and then it will form a polyamide, which is the nylon 6,6, and it's a condensation reaction. Okay, all right, now let's move on now to the sixth question. And the sixth question says that the principle of column chromatography is based on the ability of the constituents to react with the solvents in the column, react with each other in the solvents in the column, dissolve in each other in the column, move at different speeds in the column. So what do you think the right answer is to this particular question? Just look at the options that we have and let me know in the comment section what you feel the right answer is. Okay. All right. So the answer is actually D. It moves at different speed in the column. So so the principle of column chromatography is based on the ability of constituents to move at different speed. It is this difference in their speed of movement on the column or in the column that determines their separation and facilitates their separation into their components, into their varying components. So chromatography separates components based on their different rate of movement through a medium due to differences in their affinities to the stationary and mobile phase. Okay, So that's the reason, and that's why we have that as the answer. Okay. All right. So the seventh question says that ammonium chloride can be separated from its mixture with common salt by, is it A, through distillation, B, evaporation, C, decantation, or D, sublimation? Don't forget that ammonium chloride is a substance that can, okay, if I say this now, I'm telling you the answer literally. So tell me what you feel the answer is in the comment section, and then I'll continue with that line of thoughts, and I'll continue with what I'm about to say. So I'll wait a bit and let's see what you have in the comment section for me. Is it A? Is it B? Is it C or D? Okay, so please let me know what you think the right answer is in the comment section. Yeah, okay. Yeah. So if you look at it critically, ammonium chloride is a substance that can actually literally move from the solid phase to the gaseous phase. You know, it can move from the solid to the gaseous phase. So just like I was saying, ammonium chloride is a substance that will literally move from the gaseous phase, and it will practically go into, I'm sorry, from the solid phase, pardon me, it will practically move from the solid to the gaseous phase. So the right answer to this is D, which is sublimation. And the reason I provided, when you eat, upon eating ammonium chloride, it will turn directly from solid to gas, unlike common salt, which remains solid. These physical properties allows for their separation. So it can be separated out because it will sublime and then it will leave the salt behind. So by so doing, you can easily separate them. Okay, so we move on to the next one now. I will look at question number 8 that says that the ability of carbon to form long chains is referred to as the alkylation, acylation, carbonation, or catenation. Carbonation, acylation, alkylation, or catenation. So what do you think the answer is to this? Let me know in the comment section. And apart from carbon, there is this other compound or this other element too also has that slight ability. I think sulfur, yes, sulfur too has that ability, to form long chains. And this particular phenomenon is referred to as decatenation. Is catenation. So catenation is the self-linking property of carbon atoms through covalent bonds to form long chains and complex structure. This is the basis for organic chemistry, actually. Okay, so this is the basis for organic chemistry, and this is how we get organic compounds, so to speak. Okay, all right. So the next one is question number 9 that says that the industrial preparation of hydrogen gas from water gas is referred to as, is it the Bosch process, the contact process, the Haber process, or the Bayer process? So let me know what you feel is the right answer in the comment section below. Okay, all right, okay, all right. Now, this is the answer. It is called the Bosch process, and the Bosch process involves reacting water, gas, a mixture of carbon 2 oxide and hydrogen with steam to increase hydrogen yield by the water gas shift reaction. So it is the Bosch process, please. Let's take note of that. The 10th question says that the relative atomic mass of a naturally occurring lithium consists of 90% of 7 mass molecular mass of 7 and atomic mass number of 7, atomic number of 3, and then 10% lithium 6 3, mass number 6, atomic number 3. So we are asked that the relative atomic mass of a naturally occurring lithium consisting of these will be what now? Is it 6.2, 6.8, 7.1, or 6.9? Okay, now the answer is 6.9, and basically what we do is that naturally occurring lithium is a mixture of lithium 6 and lithium 7 isotopes. The weighted average is approximately 6.94, which is 6.9. How did we come about that? All you need to do is to do a 90 multiplied by 7 divided by 100, and then plus 10 multiplied by 6 divided by 100. So when you do that calculation that way, you end up having about 6.94, and which can round it up to 6.9, because 4 is not up to 5. So So it can be rounded up to, or it can become approximately 6.9. Okay, so that's how we come about that particular one. The next question says that the color of litmus in an alkaline medium is, the color of litmus in an alkaline medium is it red? Is it yellow? Is it pink or blue? What is the color of litmus in an alkaline medium? So we talked about this when we talk about acid, base, and salts, So if you can still remember that lecture, then you should be able to answer this particular question, okay? So the answer is actually blue. Litmus paper will always be blue, in alkaline medium. That is, if you bring a red litmus paper, you get a blue in an alkaline medium. So litmus paper turns blue in alkaline solution and red in acidic solution. This is a standard acid base indicator of behavior. Okay. The next one says that the compounds CH3, CH2, CHO, and CH3, CO, CH3 can be distinguished from each other using A, dilute ammonia, B, Benedict solution, C, Toland's reagent, and D, sodium hydroxide solution. Now, so how can we differentiate between a ketone and an aldehyde? That's basically what this question is talking about. How do we distinguish between a ketone and an aldehyde? And one of the ways we do that is through the Toland's reagent. That's C, the Toland's reagent. It's a distinguishing substance or reagent that we can use to differentiate between an aldehyde and a ketone. So CH3, CH2, CHO is an aldehyde, and CH3CO, CH3 is a ketone. Tolin's reagent oxidizes aldehyde to carboxylic acid and forms a silver mirror, but it does not react with ketones. So with ketones, it does not react, but with aldehyde, it doesn't react. So that's one way we can distinguish it. Okay, so on to the next one now. We can also use Fehling's test, actually, Fehling's solution, but that's not the purview of this question. So for this question, we should remember Toland's reagents. Okay, let's move along now and talk about question number 13, which says that which of the following statements is true about 2-methylpropane and butane? 2-methylpropane and butane. A, they have different number of carbon atoms. They are members of the same homologous series. They have the same boiling points. They have different chemical properties. So you let me know what you feel the right answer is from the options listed there. Okay, so the answer is that they are members of the same homologous series, B, that's the answer. And the reason is because both are alkanes, C4H10, and structural isomers. Yes. 2-methylpropane is just a structural isomer of is an isomer of butane. So hence they belong to the same homologous series. So they are both alkanes. They belong to the same homologous series. Okay. 14 says the process that requires the use of hard water in its operation is tanning, bottling, laundry, dyeing. So please let's look at the options carefully and let's see, which of the process requires the use of hard water. Okay, so the answer to this one is actually tanning. Yes, it's tanning. It's tanning, and the reason is because hard water is rich in calcium and magnesium ions, which are traditionally useful in tanning process, aiding in the cross-linking of collagen in hides. So that's why it is useful in the tanning process. Okay, all right. So let's move on now to the question number 15, which is what is the concentration of a solution containing 2 grams of sodium hydroxide in 100 cm cube of solution? Okay. The options are A, 0.05 mole per dm cube, 0.30 mole per dm cube, 0.50 mole per dm cube, 0.40 mole per dm cube. So let's look at what you feel the answer will be. Please don't forget, always put your what you feel your own answer is in the comment section. It will I'll be able to know whether you got most of the things that we treated in the syllabus, and now having questions to answer, if you can apply that same knowledge to answer this question. It's a pretty simple question, Just need to understand and interpret right, then apply the right, formula or process that will give you the solution. Okay, so the answer to this is 0.50 molar. And how did we arrive at this now? The molar mass of sodium hydroxide is forced, bringing out the relative atomic masses together. So you add them up together, you get 40 gram per mole. Okay, the moles of sodium hydroxide is 2 grams divided by 40 gram per mole, which will be equal towards 0.05 mole. Now, the volume that was used is 100 cm cube. We convert that to dm cube, and that will be what 100 divided by 1000. That's 0.1 dm cube. Now, concentration equals to what mole divided by the volume. That's why we said mole per dm cube. Okay. So now the mole of sodium hydroxide as calculated is 0.05 mole. We've calculated that. The volume as calculated is also 0.1 dm cube. So when you do the division, you end up having 0.5 mole per dm cube as your concentration. Okay, so that's pretty straightforward and simple. Okay, let's move along now and look at another question. It says that the radioisotope used in industrial radiography for the rapid checking of faults in welds and casting is phosphorus 32, cobalt 60, carbon 14, iodine 131. So which of these do we use to check for faults in welds? Okay. Okay. Yes. All right now. So the answer to this one is cobalt 60. Cobalt 60. And the reason is because cobalt 60 emits gamma rays and it is used to inspect metal castings and welds for structural defects. Okay, all right now. So we move along now to the next question that says that the compound produced when sodium peroxide is heated with excess sodium is, the compound produced is Na2CO3, Na2O, NaNO2, NaOH. So what is the compound that is produced when sodium peroxide is heated with excess sodium? So let me know what you feel the answer is in the comment section. Okay, so yes. All right now. Okay, yes. So let's move on now. The answer is B. Na2 is the answer, and we can have an equation to back it up. And apart from that, when sodium peroxide is heated with excess sodium, the peroxide decomposes, forming sodium oxide. And that's what we have there with that equation that is quite explicit, So that's the answer to that. Okay. Question number 18 says that the pollutants that contribute to the depletion of the ozone layer is a CFC, carbon fluorochloride or so. Is a CFC. I think that's the right word. Yes. Yes, NO2, SO2, or CO2. The answer to this one is actually carbon fluorocarbon. Thank you. This chlorofluorocarbon. I think I'm mixing it up. I'm bringing the other one forward and taking the other one backward. Pardon me about that. And the brain can be funny sometimes. So it is chlorofluorocarbon. Chlorofluorocarbons, not carbon fluorochloride. All right, don't mind me. So it is chlorofluorocarbons, which is the CFCs. They are very, very terrible, and they deplete the ozone layer, and that is one of the reasons why we have ultraviolet radiations, coming in amounts that can be very, very harmful to us as humans. You understand? So it is chlorofluorocarbons, and then that's the answer. So CFC release chlorine radicals in the stratosphere that catalyze the destruction of ozone molecules. Okay, so that's the reason why we have that. So it's a very terrible pollutant, and all effort is being made globally to ensure that the use of chlorofluorocarbons, especially as refrigerants and all that, is highly sanctioned to guide against um, the depletion of the ozone layer, and it's used in so many industrial processes, and this has been banned and been frowned again. Most of the environmental summits that we've had, global environmental summits, they discover that they discuss this very well, because it is causing great harm to the environment, causing so much harm, and that's why we have the ultraviolet radiation that are not in the quantity that are supposed to be interfacing with the human body. And apart from that, it affects even the glaciers. We see the ice melting and then resulting in flooding and tsunami and so many other things like that, and it caused so many destruction globally. So we should be mindful of these, and we should also ensure that we are an advocate wherever we find ourselves, so that our ozone layer can be protected. Okay. All right, let's move on to the next question that says that which of the following properties is not peculiar to matter? Which of the following properties is not peculiar to matter? A, kinetic energy of particles increases from solid to gas. B, random motion of particles increases from gas to solid. C, orderliness of particles increases from gas to liquid. And then random motion of particles increases from liquid to gas. So what's the answer? The answer is actually B. Random motion of particles increases from gas to solid. And the reason is the reason why this is incorrect is because, in fact, random motion of particles decreases from gas to liquid to solid, and that's it. Because there's more randomization of particles, as in movements in the particles, in the gaseous phase compared to the liquid phase. In the solid phase, it's even very highly limited compared to all the two other phases. So this is one item that is not correct. So that's B. Random motion of particles increases from gas to solid is incorrect. Okay, so we're moving along now to question number 20 that says cast iron is used in making what now? What do we use cast iron for? Is it chains and agricultural implements, iron sheets and retort stand, nails and iron rods, stoves and cooker? So what do we use cast iron for? So let me know what you feel the answer is in the comment section. Okay, while I reveal to you what the right answer is, and then what the explanation for choosing that particular answer. Okay. Chains and agricultural implements, that's what we use cast iron in making. And the reason is because cast iron is hard and brittle and is often used for making heavy duty items such as machine parts, chains, and plowshares. So that's what we use cast iron for, because they are hard, then they're also brittle too. Okay. So the next one says that which of the following compound is used as a gaseous fuel? Which of the following compound is used as a gaseous fuel? So let's look at the options one after the other, and let's come up with the right answer. Which one of them is used as a gaseous fuel? Okay. All right. So going by these, the answer to these is actually propine. As saying propine. That's C3. Excuse me, please. Pardon me. Okay. CH3C, triple bond CH. So that's propine, and that's option B. So propine is an alkyne and a gaseous hydrocarbon commonly used in welding torches as a fuel due to its high flammability and energy content. Okay, all right. So that's that for that. So moving along now to the next one says that the product formed. Just a minute. It says the product formed when primary alkanols are oxidized using acidified potassium tetraoxomanganese 7 are what? What are the product formed when you oxidize primary alkanols? So is it A? Is it B? Is it C or D? So please let me know in the comment section what you feel the right answer is. Okay, so for this one, the answer is actually CH3COH and CO2. Okay, so when you use this, it gives us ethanoic acid, especially if it is like ethanol that was oxidized using KMNO4. So you have CH3 plus to CO2. So primary alkanols are first oxidized, yes, to aldehyde. That's the first step. And further to carboxylic acid. With prolonged oxidation, carbon dioxide and water may form. or may be formed in a control oxidation. CH3COH ethanoic acid is expected. So that's the answer to that. Okay. Alkanols have the general molecular formula CnH2n minus 2, CnH2n plus 2 CHO, CnH2n minus 2 OH, and then CnH2n plus 1 OH. Okay. Okay, let me just give you an expo here and tell you that the answer lies between option C and option D. So what do you think the answer would be like based on that? Little insight I've given to you now. Okay, if you look at it critically, you discover that the answer to this should be D, which is CnH2n plus 1 OH. That's their general molecular formula. So it's alkanols, or alcohols are derivative of alkanes, where one hydrogen atom is replaced with hydroxyl group, given the general formula CnH2n plus 1 OH. All right. So the next one says that which of the following is not an alkali? An alkali, an alkali. Okay. Is it calcium hydroxide, ammonia, sodium hydroxide, or aluminum hydroxide? Which of them is not an alkali? Alkalis are soluble base. They are soluble. Okay. So the answer is AlOH3 and aluminum hydroxide. And the reason is because aluminum hydroxide is amphoteric. Amphoteric, please. It can act as both acid and base, but it is not a strong alkali like sodium or ammonia or even calcium hydroxide. And that is the reason. And it is, okay, so that's the reason. So please, let's take note of that. Question number 25 says that which of the following statement is correct about the periodic table? Elements in the same group have the same number of electron shells. The non-metallic properties of the element tends to decrease across each period. Elements in the same period have the same number of valence electrons. The valence electrons of the elements increase progressively across the period. So what do you think the right answer is to this particular question? So please let me know what you feel the right answer is in the comment section. Okay. Oh, okay. All right. Now, okay. Oh, all right. Let's go down. So the right answer is the valence electrons of the elements increase progressively across the period. That's very, very correct. As you move from left to right across the period, the number of valence electron increases by 1 in each successive element. Okay. So question number 25 says that the metal whose ore can be concentrated by passing it through a magnetic separator is zinc, tin, copper, or calcium. So what do you think the answer is to this one? So please let me know. Let me know in the comment section what you feel the answer is. I'll wait a bit for you to come up with your own answer before I reveal mine. Okay. All right. So okay, so this is the answer, and we have it here. Zinc is the answer, and the reason is because zinc ores like zinc blende, which is zinc sulfide, are not magnetic, but some ores, e.g., the magnetite in iron, can be concentrated using a magnetic separator. However, if the question concerns separating zinc from other impurities like magnetic properties, the magnetic separation can sometimes be employed. So zinc is the right answer here, please. Moving along, an example of an acidic oxide is it NaCO, SO2, or copper oxide? So the answer to this one is SO2, okay? And SO2 will give us sulfur dioxide. Is a typical acidic oxide. It reacts with water to form sulfurous acid. Okay, so we move on to the next one. What volume of 0.5 molar H2SO4 will exactly neutralize 20 cm cube of 0.1 molar sodium hydroxide solution? So these are the options that we have. And let's look at the solution now. Now, the correct answer to this one is actually 2.0 cm cube. And the reason is, first and foremost, we look at the equation for the reaction. So what you see there is that there's a reaction ratio of 1 to 2, 1 for the acid and 2 for the base. So that you need 2 moles of sodium hydroxide to react with 1 moles of the acid. So we now bring in that formula that says that C1V1 over C2V2 equals to N1 over N2. So when you cross multiply, you end up having an equation like a C1V1 divided by N1 equals to C2V2 divided by N2. So when you do that and you flesh it out, you end up having what? 2.0 cm cube. 2.0 cm cube. So let's take note of that as we move on. Diamond cannot be used in making bicycles, as abrasive, in cutting glass and metals, as ties for drawing wires. So diamond cannot be used for. Which one can we not use diamond for? That's what the question is asking us basically. So looking at it critically, the answer to this is that in making bicycle chains, you cannot use diamond for make bicycle chains. So diamond is hard and brittle, unsuitable for load bearing or flexible component like chains. It's ideal for cutting tools and as abrasive. So that is what we use diamond for. So please let's take note of that. Okay, so that's that for that. So diamonds they are hard and brittle, they are unsuitable for load bearing or flexible component like chains. So it is ideal for cutting as a cutting tool or as abrasives. Okay. So let's move on to the next one that says that ethanol is soluble in water. Ethanol is soluble in water due to the presence of is it a carbonyl group, hydroxyl, is it a carbonyl group, an hydroxyl group, a phenyl group, or a methyl group? So why is it soluble in water? Please put what you feel the answer is in the comment section. So the answer to this one is actually B, hydroxyl group, and the hydroxyl group forms hydrogen bond with water, forming ethanol, making ethanol highly miscible, with water. Okay. So question 30 says that the number of electronic shells contained in an atom with electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2 is. So what is the number of electronic shells that we have there? Is it 3? Is it 2? Is it 4 or 5? So please let me know what you feel the right answer is in the comment section there. Okay. Okay. All right. Now, so the answer is actually 4. And how did we arrive at that? Each number before the orbital letter, that is 1s2s, etc., represent the principal energy level. It can be principal quantum number, azimuthal quantum number, spin quantum number, magnetic, and so on and so forth like that. So a shell in this configuration, we see electrons in first shell, that's 1s. We also saw electrons in second shell, which is the 2s and the 2p. And then in the third shell, which is the 3s. Excuse me, please. Excuse me. In the third shell, where we have the 3s and the 3p, and then in the fourth shell, we also saw electrons, 2 electrons to be precise, in the 4s orbital. So there are 4 shells in all. So it's a total number of 4 shells. Okay. All right. Now, so the answer there is 4. Question number 32 says that the drying agent suitable for drying ammonia is A, calcium chloride, B, calcium oxide, C, phosphorus oxide, D, concentrated H2SO4. Now, one critical thing that you must take note of here is that you must look for a drying agent that will not react with ammonia. That it will dry it and it will not react with it. So you have to be very careful in the selection of the type of drying agent that you're going to use, bearing in mind that particular fact that you need one that will not react, with ammonia. So let's look at it together. Is it calcium chloride? Is it calcium oxide, phosphorus 5 oxide, or concentrated H2SO4? So the answer to this one is actually calcium oxide. Now, the reason is because, like I said before, to choose a suitable drying agent for ammonia, we need a substance that removes moisture and that does not react with ammonia. And calcium oxide is a perfect, drying agent in this regard for for drying ammonia. Okay. So, so like I said, calcium oxide will absorb moisture efficiently. It does not react with ammonia, and it is suitable for drying ammonia. Okay, so that's that for that. So moving along now to question number 33, it says the arrangement of particles in crystal lattice can be studied using X-rays, beta rays, alpha rays, or gamma rays. So what is the answer, please? All right. Okay. So the answer to this one is actually X-rays. And the reason why we chose X-rays is because X-rays have wavelengths that are similar to the distances between atoms in a crystal. So when X-rays are directed at a crystal, they are diffracted by the atoms in the lattice. So the resulting diffraction patterns can be analyzed to determine the atomic structure of the crystal. So that's the reason why we chose, excuse me, please. We chose X-rays. Okay. 34 says that in the extraction of iron, the waste gas from the furnace is a mixture of, is it phosphine, carbon 2 oxide, and carbon 4 oxide, carbon 4 oxide, and carbon, nitrogen, carbon 2 oxide, and carbon 4 oxide, of phosphine and carbon 2 oxide. What is your answer, please? Put them in the comment section and let's see whether you're right or you're wrong. Okay, all right. Now, so the answer to this one is actually nitrogen, carbon 2 oxide, and carbon 4 oxide. Now, the reason why we chose this answer is what I've stated here now. Now, the main reaction inside the blast furnace is we have calcium with, carbon will react with oxygen to give us carbon 4 oxide. Carbon 4 oxide will react with carbon to give us carbon 2 oxide, 2 molecules of carbon 2 oxide. Then the iron ore itself, or the iron rather, will react with carbon 2 oxide, 3 molecules of carbon 2 oxide to give us iron, and then 3 molecules of carbon 4 oxide. So the waste gas commonly released include, carbon monoxide, carbon dioxide, and nitrogen from the from the blast used for combustion. So this is what we see happening most times. Okay, so please let's take note of that as we move on to the 35th question that says that in the neutralization reaction involving HCl and sodium hydroxide using litmus as an indicator, the color at the endpoint is A, blue, orange, B, red, C, orange, and D, purple. So please let me know what you feel the answer is in the comments section. And I reveal to you what the answer is and the reason why I'm choosing that as my own answer. Okay, so the answer to this one is actually purple. Purple. Okay. Litmus indicator behavior. In an acidic solution, it is red. In basic solution, it is blue. At neutral pH, around 7, purple. And this is like an intermediate between red and blue. So what we should expect, the color at the endpoint will be purple. So let's take note of that. So therefore, at the endpoint of neutralization, reaction between HCl and sodium hydroxide, the solution becomes neutral and the litmus turns purple. Okay, all right. So we'll move now to the next question that says an example of a solid emulsion is A, butter, B, air, C, milk, D, cod liver oil. So if you look at this critically, you'll discover that the answer lies between A, B, and C. Cod liver oil is not an emulsion, so it's not even part of the the options that we are going to consider seriously. So the serious contender for the answer should be between options A to C. So please look at it carefully and tell me, what do you feel the right answer is in this regard? Okay, all right. See, so from my own standpoint, the right answer is A, actually, that's butter. And the reason why we are choosing A is simply because of the fact that, when we talk about solid emulsion, we are talking about an emulsion where the disperser is a liquid and the dispersion medium is a solid. And if you look at butter is a solid emulsion. Why? Because water droplets disperse in solid fat. Water droplets are dispersed in solid fat. So If you look at it, the dispersion medium, we have solid, which is the fat, and then the dispersed phase, which is liquid, and that is water. So that is what makes water a perfect answer to this question that we have here. All right, now on to the next one. An isotope has an atomic number of 15 and a mass number of 31. The number of proton it contains is it A 16? Is it A 16, B 15, C 31, or D 46? So please let me know. Let me know what you feel the answer is in the comments section. Okay, so please look at it critically and let me know what you feel it is in the comments section. Okay, the answer is B, 15. And how did we arrive at that? Now, if you remember closely, when we talk about mass number, atomic number, like that, in one of our lessons, when we're treating the JAM syllabus, one of the things if you can recall vividly is that we said the atomic number is synonymous to the proton number. You can still recall that, right? Yes, exactly. So if you have an atomic number of 15 and a mass number of 31, so by extension, the proton number should be 15, and that's what I just tried to use this to explain. So atomic number is equal to the number of protons, mass number is equal to protons plus the neutron. If that is the case, the atomic number will be equals to 15 because it's the atomic number is 15. Therefore, the number of protons will also be 15 because of that. Because of what you have stated earlier, the atomic number is equals to proton number. Okay. All right. Now let's move on now to the next one. It says calculate the volume in cm cube of oxygen involved at STP when a current of 15 amperes is passed through acidified water for 193 seconds. So Faraday constant equals to 96,500 molar volume of gas at STP is 22.4 dm cube. And these are the options that we have. So please, let's work it out and let's see what we can arrive at. So I'll give you a little time to work it out and tell me in the comment section what you feel the right answer is. Is it A? Is it B, C, or D? Okay, all right, see? So, so going by that calculation, what you discover is that the answer to this is actually A, 0.056 dm cube. How did we arrive at these particular answers? Going stepwise now, you discover that we calculated the total charge, which is Q, and Q equals to current multiplied by time. The current that we are provided with is 5 amperes, and the time is 193 seconds. So the charge Q will be equals to 965 coulombs. Okay. The second step is to look at the equation, the half reaction at the anode, where oxygen is involved, So when you do this, you have this. This shows that 4 moles of electron produces 1 mole of oxygen. So 1 mole of oxygen equals to 4 times 96,500, which is about 386,000 coulombs, okay? Having said this, the next thing that we need to now touch on is the moles of oxygen produced, which will be 965 coulombs, as calculated from the charge, divided by the, what's it called? The moles of 1 moles of oxygen, which is like from that particular equation that we just had up there, which is divided by 386,000 that we calculated earlier. So the number of moles of oxygen or the moles of oxygen will be 0.0025 mole. Now, the volume of oxygen at STP is will be 0.0025 moles multiplied by 22.4 dm, which is the standard volume at STP. So it means that you end up having a volume of about 0.056 dm3. That is what volume of oxygen that we involved at STP. So let's take note of that. And the option there, or the right option, is option A, 0.056 dm3. Okay. So this one says that the gas that is used for the treatment of cancer. The gas that is used for the treatment of cancer is A, neon, B, random, C, xenon, and D, argon. So what is the gas that is used for the treatment of cancer? Okay, let's just look at them together. The answer is actually radon. And why do we choose radon? It's because one, radon is radioactive noble gas. It emits alpha particles, which can be used in radiotherapy to destroy cancerous cells, Although it's used as decline due to safety concern and better alternative, radon was historically used in the treatment of certain types of cancer. Neon is not the answer. It's mostly for lightning, neon light and all that. Xenon is always used as an anesthetic and also in the world of medical medicine, for um for doing radiological, activities, and then argon, almost the same thing too. So the answer there is actually radon, and the reason is because it is used to destroy the cancerous cell. Although, like it stated, other alternative are sprang forth. So it's not something that we keenly use like before, and majorly also because of the safety concerns around using of random. Okay, so we move now. A chemical reaction in which the hydration energy is greater than the lattice energy is referred to as A, reversible reaction, B, spontaneous reaction, C, an endothermic reaction, D, an exothermic reaction. Okay, the answer to this one is an exothermic reaction. An exothermic reaction. That's the answer. And the reason is because if hydration energy is greater than lattice energy, then more energy is released by hydration that is required to break the ionic lattice or lattice. So the overall energy charge is negative, or no, overall energy change is negative, meaning the process releases energy, and that is an exothermic reaction. Okay. So this one says that MnO4 plus Y plus 5Fe2 to give us MnO2 plus F5Fe3 plus 4H2O. So, and the equation about Y is it 10 hydrogen, ion, or 5 hydrogen 8, or 4, as the case may be. So we are looking for Y, which we don't know. And this is just balancing redox equation, and this is balancing in the acidic medium. So when you will look at it and we reflect on the steps that I shared with you when we're treating balancing redox equation, you can actually figure out what Y is. So what you need to do, divide them into two half cells, an oxidation half cell, the reduction half cell, then try and balance, in terms of their atoms. Then after balancing, balance in terms of electronically, as in terms of the electrical charges, and then after that, do the same thing for oxidation half cell and the reduction half cell. Then you combine them, try to cancel out the number of electrons by multiplying with appropriate values and all that. So when you go through the old works like that, you'll end up having your answer to be C, which is 8 hydrogen ion that should be added, which is Y, that is not known, So it is 8H plus, that is Y. And like I said, bringing it out like this is a stepwise thing. You drop them into two half reactions, reduction, and then the oxidation. And then when you move on like that, you have that you combine, and then you can easily get what Y is, which is the unknown entity in that question. So 8H plus, that's what Y represents there. Okay. So we have this, and we are asked this question. Just a minute, please. Okay. So we are asked the question below. The compound above exhibits A, geometric isomerism, B, position isomerism, C, structural isomerism, and D, optical isomerism. So you tell us what you feel the answer is to that. Let me put this one in the center. Okay, so the correct answer is optical isomerism. Why? The reason is what we have here. The reason why we say it is optical isomerism is what we have here. Now, the given compound is lactic acid, which contains a chiral center. The central carbon atom and is bonded to 4 different groups. That's what we mean by chiral center. The central atom is bonded to 4 different groups. You can have the methyl group on one side, you have the hydroxyl group bonded, you have the carboxylic acid group bonded, and then you have the hydrogen atom that is also bonded to that central atom, which is the chiral center or the chiral carbon, as the case may be. Now, when you look at that, you discover that because the carbon has 4 different substituents, it is a chiral center, making the compound optically active. It can exist in 2 non-superimposable mirror image form, that is, which we call enantiomers, which is the hallmark of optical isomerism. Okay, so that particular compound up there will exhibit optical isomerism. Okay. So we move along now. Pardon the the position of the P and the Q. The P is just supposed to be directly above where we have the forward and the backward reaction. And the Q is under where we have the forward and backward reaction. So what we have here is air, the monosaccharide, a reversible reaction giving us a polysaccharide, and then and water. So in the process above, P and Q respectively represent what now? Is it A, condensation and hydrolysis? B, fermentation and condensation, C, polymerization and hydrolysis, or D, polymerization and condensation. Now, when you look at this critically, you discover that what is happening is actually a monomer proceeding to give us a polymer. So from this, you can actually have an inkling that, okay, the right options that I should be seriously considering as an answer to this question is either C or D. Okay. If that is the case, we now need to look at the second thing, which we are going to review with the answer. So it's actually polymerization and hydrolysis. And the reason for that is because of the P, which is the forward reaction, is a polymerization reaction. When monosaccharide, e.g. glucose, join together to form polysaccharides like starch or cellulose, releasing water, and that is what we call a condensation polymerization. Now, Q, which is the reverse reaction, is hydrolysis, where water is used to break down the polysaccharide back into the monosaccharides unit. So you discover that the forward is a polymerization reaction, the backward is an hydrolysis reaction. Okay, so we'll move along now to the next one and see question number 44 that says that the functional group present in the compound above are, what are the functional groups that we can say is present in this compound? Alkenes and allo group, hydroxyl and chloro group, alkenes and chloro group, and hydroxyl and allo group. So the answer to this one is actually D, hydroxyl and halo group. But there's one that looks similar too, which is the hydroxyl and chloro group. But the reason for not choosing that as an option is what I've stated below here. Now, option B is also essentially correct, but option D uses proper terminology. So the difference is just in their terminology now, which is more general and matches the wording of the question. So halo group in this regard it's a more matching and fitting term to use compared to chloro group. So option D is the right answer and not option B. Thank you. So we look at the next one that says that energy, then you should have an energy profile like that, that the energy diagram profile. Okay, so we have reactant, then we have the product, and then the reaction coordinates and all that. So in the diagram above, S is it enthalpy, B, activated complex, C, activation energy, D, enthalpy change. So what does X represent? What does X represent? If you look at it, X represents the enthalpy change. And why do we say that? And the reason is because X represents the energy difference between the reactants and products, which is the enthalpy change, delta H of the reaction. Okay. All right, now. Moving on to the next one, look at this diagram again. The diagram represents A, spontaneous reaction, B, an exothermic reaction, C, a non-spontaneous reaction, D, an endothermic reaction. So look at it carefully. What do you think the right option is in this in the option listed below? For me, it is actually B. It's an exothermic reaction. Why is it an exothermic reaction? If you look at the diagram, the reactant starts at a higher energy level than the products. This indicates that energy is released as the reaction progresses. Therefore, the overall enthalpy change, delta H, is negative. This is characteristic of what? An exothermic reaction. So please let's be mindful of this. Okay, all right now. So we move now to the 47th question that says that the curve depicts titration between a strong acid and a strong acid of pH. So it says, what does this curve depict rather? Between a strong acid. So what does it depict, this particular curve that we have there? The first one is saying that it's a strong acid and a strong base. The second one is a strong acid and weak base. It shows a weak acid, titration between a weak acid and a weak base, and titration between a weak acid and a strong base. Well, if you look at it critically, you discover that the curve is quite unique, you know, and it can definitely not be between a weak acid and a weak base. Neither can it be between a weak acid and a strong base, you know, because of the inflection point and the way the curve is shaped. So based on these, the right answer to this should be A. Yeah, strong acid and a strong base. That's the right answer there. And the reason is because the pH curve in the diagram shows the following characteristics. Now, initial pH is very low. That is, the pH is between maybe 1 and 2, showing the following characteristics. Now, initial pH is very low. Like I've said that, I said it's approximately between 1 and 2, indicating a strong acid. There is a sharp rise in pH near the equivalence points. You know, the equivalent point is at the point where you are getting to about 7.7, you understand? Now, the equivalent point occurs around 7, which is neutral. So a strong acid and a strong base titration results in a sharp vertical rise and an equivalent point at 7. So this particular curve fits, you know, a titration between a strong acid and a strong base. So we need to understand that and establish that now. So that is what that curve represents or depicts. Okay. So we'll look at another one again. From the diagram above, an ideal gas can be represented by, is it K, is it M, is it L, or N? Now, let's try and respond, but the right option to this should be N. N, yes, it should be N. That's option D. And the reason is because when you look at an ideal gas, from the ideal gas, PV equals to what? nRT. We still remember that, right? Okay. Now, at constant temperature and amount of gas N, the product PV remains constant regardless of pressure. That is what the ideal gas law, you know, stipulates or states. So at constant temperature and an amount of gas N, the product's PV remains constant regardless of the pressure. Now, this means that the graph of PV versus P for an ideal gas should be a horizontal straight line. That is, PV is constant. It's not deviating, it's not fluctuating, you understand? So PV is a constant, okay? From the diagram, curve N is a horizontal line, indicating PV is constant with changing pressure. This matches the behavior of an ideal gas. So it matches the behavior of an ideal gas. And so that's why we chose option D, which is N on that diagram. Okay, so looking at this equation, it said the major factor that influences the rate of reaction above is it concentration? Is it catalyst? Is it temperature? Or is it light? Look at that equation closely and you know that that equation looks like something that will need, okay, let me allow you to respond in the comment section before I come up with the answer and explain why the answer is that. Okay, so we have, okay, all right now. The answer is actually light, which is D, and the reason is because this is a chlorination reaction, specifically a substitution reaction of methane with chlorine. This type of reaction is known to proceed through a free radical mechanism. A free radical mechanism. So free radical halogenation of alkanes like methane or methane rather requires ultraviolet light or sunlight to initiate the reaction by breaking the chlorine-chlorine bond homolytic fission. Okay, so that's that for that. So let's take note of that. The last question that we are looking at, which is the 50th question, is in the reaction above, an increase in temperature will A, increase the reactant production, B, increase the value of the equilibrium constant, C, shift the equilibrium to the left, and D, decrease the value of the equilibrium constant. Okay, so let's look at the option carefully and tell me which one do you feel will be the right answer here now. Okay, all right, okay, all right now. Yes, 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 yes. So the right answer here is actually option B, increase the value of equilibrium constant. It increases the value of equilibrium constant. Why is that? For an endothermic reaction, which this reaction is because delta H is positive. So for an endothermic reaction, increasing temperature shifts the equilibrium to the right, increasing the concentration of products, which increases the equilibrium constant. So that is the reason why we are choosing, or why we have chosen this particular option that we chose. All right. Thank you for listening, and thank you for participating in this solution to the 2016 JAM Chemistry past question. So I will continue again with 2017, and we'll go on like that later. So I'll see you in the next video. Thank you once again.